All right, class, settle down, settle down. Welcome back to Software Development Fundamentals. Today, we're diving into the heart of almost every modern application, the database. We've talked about application logic and user interfaces, but where does all that valuable information reside? That's right, in our Database Management System, or DBMS. This session is all about taking our theoretical data model, the blueprints we designed, and bringing it to life. We'll be covering building the database, creating database objects, manipulating data, and critically defining data security schemes. Get ready for a lot of technical terms, as these are the precise words you'll use when collaborating with database administrators, DBAs, and other developers. Good morning, future software architects. Today's mission is to translate our abstract data model into a concrete, functional database. This is where your application's data will live, so getting it right is paramount. We're moving from diagrams to actual data storage. Recall our previous lessons on data modeling. We designed our entities, defined their attributes, and established relationships between them, one-to-one, one-to-many, many-to-many. This visual representation, often an entity relationship diagram, ERD, is our guiding star. Now we're going to use this blueprint to build the database for the software. The primary language we'll use for interacting with our database is SQL Structured Query Language. It's the lingua franca of relational databases. Our first step is typically to create the database instance itself within our chosen DBMs. For example, in PostgreSQL, you might use the create database command, create database sales _management _DB. Once the database instance exists, we connect to it. Now we're ready for our second major topic, creating database objects. Based on our data model, the most fundamental objects we'll create are tables. Each entity in our ERD becomes a table in our database. Each attribute becomes a column within that table, with a specified data type. Varchar for text, integer for whole numbers, decimal for monetary values, Boolean for true, false, date or timestamp for temporal data, and so on. We'll also define constraints like not null to ensure data integrity, and crucial primary key constraints to uniquely identify each row. Create table customers, customer underscore ID, serial primary key, first underscore name varchar 50, not null, last underscore name varchar 50, not null, email varchar 100, unique, phone underscore number varchar 20, create table products, product underscore ID, serial primary key, product underscore name varchar 100, not null, description text, price decimal, 10-2, not null, stock underscore quantity integer not null. Create table orders, order underscore ID, serial primary key, customer underscore ID, integer not null, order underscore date timestamp default, current underscore timestamp, total underscore amount decimal, 10-2 not null, status varchar 50, default pending, foreign key, customer underscore ID, references, customers customer ID. Notice the foreign key constraint in the orders table. This establishes the relationship between orders and customers, enforcing referential integrity. This means an order cannot exist without a valid customer. Beyond tables, we might create other database objects to enhance performance and functionality. For example, indexes are critical for fast data retrieval. They're like the index in a book, allowing the DBMs to quickly locate specific rows without scanning the entire table. Create index, IDX underscore customers underscore email on customers, email. Create index IDX underscore orders underscore customer underscore ID on orders, customer underscore ID. We also create views, which are virtual tables based on the result set of a SQL query. They simplify complex queries and can provide a level of data abstraction and security. Create view. Active customers as select customer underscore ID, first underscore name, last underscore name, email from customers where customer underscore ID in, select distinct customer underscore ID from orders where order underscore date, January 1st, 2024. And for encapsulating business logic, we use stored procedures or functions. These are pre-compiled SQL statements that can be executed repeatedly, improving performance and maintainability. They're excellent for complex operations or for enforcing business rules at the database level. Once our structure is in place, we move to manipulating data in the Database Management System, DBMS. This is where our application truly interacts with the database, performing the CRUD operations: create, read, update, and delete. To create new data, we use the insert statement. Insert into customers, first underscore name, last underscore name, email, phone underscore number, values, Alice, Smith, alice.smith@example.com, 555, 1234. Insert into products, product underscore name, description, price, stock underscore quantity, values. Laptop Pro X, high performance laptop 1500.00, 50. To read or retrieve data, the select statement is our workhorse. We can fetch all columns or specific ones, filter rows using a where clause, sort results with order by, and combine data from multiple tables using join operations, an absolutely essential skill. Select from customers, select product underscore name, price from products where price, 1000. Select c.first underscore name, comma c.last underscore name, comma o.order, underscore id, comma o.order underscore date, from customers. C join orders o on c.customer underscore id equals sign o dot customer underscore id, where o dot status equals sign pending. To update existing data, we use the update statement, always specifying a where clause to target the correct rows, otherwise you'll update everything. Update product set stock underscore quantity equals sign 45. Where product underscore id equals sign 1, update, customer set phone underscore number equals sign 555 9876, where email equals sign alice.smith@example.com. And finally, to delete data, we use the delete statement. Again, the where clause is crucial to prevent accidental data loss. Now let's talk about an absolutely non-negotiable aspect of database management: defining data security schemes. This is paramount. Data breaches can lead to catastrophic consequences, from financial losses to reputational damage and legal issues. We need to control who can access what and what they can do with it. Most DBMS provide robust security models. We achieve security through a combination of authentication and authorization. Authentication verifies who a user is, typically via a username and password. Authorization defines their permissions once authenticated. We typically create database users for applications and individual administrators. Instead of granting permissions directly to users, a best practice is to define roles. A role is a collection of privileges. You then grant these roles to users. We use the grant command to assign privileges like select, insert, update, delete on specific database objects to users or roles. Conversely, the revoke command removes these privileges. This least privilege principle is vital. Users and applications should only have the minimum permissions necessary to perform their functions. For instance, a sales report application only needs select access, not delete. Beyond access control, consider other security measures: encryption at rest for sensitive data stored on disk, and encryption in transit for data moving between your application and the database. Always use secure connections like SSL or TLS to prevent eavesdropping. Also, regularly review audit logs to monitor database activity and detect suspicious behavior. Implement strong password policies, and never store sensitive credentials directly in your application code. Use environment variables or secret management services. So, as you can see, building a database goes far beyond just defining tables. It involves careful design, precise SQL commands for object creation and data manipulation, and, most importantly, a rigorous approach to security. A well-structured and securely managed database is the backbone of a reliable and trustworthy software application. Your practical task for this week is to take one of your previous data models, define its tables, columns, and relationships, and then use SQL to create those objects in a local database instance. Then practice inserting, selecting, updating, and deleting some sample data. Finally, experiment with creating a new user and granting them limited permissions. Don't be afraid to make mistakes. That's how we learn. Software Development Fundamentals. Thank you for watching.